Day 124, Notes, Pre-Calculus. Today we finish our discussion on the trigonometric ratios for the week, and in order to complete this discussion I chose a series of practice problems from the back of the chapter to work on. So we'll complete 47 to 56 1 mod 2. 47 tells us that the angle of elevation to the top of the Empire State Building in New York is found to be 11 degrees from the ground at a distance of 1 mile from the base of the building. So if I'm 1 mile away and I look up at the building at 11 degrees, so imagine this is me standing all the way down here, I can look up to see the top of the Empire State Building. There's a big tower on the top. Okay, so this is me looking up at 11 degrees to find the height of the Empire State Building. I don't know exactly how tall it is, but I do know that I'm standing 1 mile away. I do recognize that this represents the opposite side length of the triangle here. So we've got an opposite side and an adjacent side. So a tangent measurement would be good to use here. Tangent of 11 degrees would be equal to x divided by 1, which means that x itself is equal to tangent of 11 degrees. Now tangent of 11 degrees can be found by using our calculator pretty quickly. So if I press Control Enter, I'll get the decimal equivalent. This is 0.19438. So we'll call that x equals 0.1944. Now it's important to recognize our units of measure here. There we go, it's miles. So the Empire State Building is almost 2/10 of a mile tall. Now we usually don't measure the height of buildings in miles, so we can convert this into feet if we'd like. If we had used the number 5,280 to represent feet out here at the beginning, then we would have used tangent of 11 degrees again equals x divided by 5,280. So x would have been equal to 5,280 times tangent of 11. And if I multiplied that result by 5,280, then we'd see that the building, Empire State Building, is about 1,026 feet tall. So I'll say that it's approximately 1,026 feet. Either answer is fine. This is probably the more traditional one that I would see for a result here, since our original measurements were given in miles. Please make sure that you include your units, regardless of the answer that you select. So here's an interesting question. I have a laser beam on Earth that's to be directed towards the center of the moon, but the beam strays 0.5 degrees from its intended path. How far has the beam diverged from its assigned target when it reaches the moon? If we know that the distance from Earth to the moon is 240,000 miles. So let's create a small diagram again. This is me standing on Earth with my laser beam, and I'm shooting it off towards the moon, which is 240,000 miles away. I'm going to exaggerate this drawing just a little bit. Again, here's our moon. Instead of shooting directly towards the center of the moon, we were off by half of a degree. So I'm going to show that over here. I'm going to create a right triangle this way. So this angle measure that I deviated from my path was 0.5 degrees. We can discover this x value here. That would represent how far I've missed my target when I'm aiming 240,000 miles away. Now that dimension is an opposite side, and we have a tangent. We have an adjacent side here, which means we should probably use the tangent rule. If I have tangent of 0.5 degrees, that would be equal to the opposite side, x, divided by 240,000. So x by itself is 240,000 times tangent of 0.5. Therefore, x would be equal to the result of that calculation. So 240,000 times tangent of 0.5 equals 2094.4. We'll go ahead and just round that to one decimal place. 2094.4. And again, our measurements were given to us in miles, so this means that we've deviated 2,094 miles from our target. Now that's the answer to part A. Part B, does the beam strike the moon? The answer is no. This moon is only 1,000 miles in its across its radius. So if I was aiming towards the center and this half of a degree difference moved my target or moved my laser 2,000 miles, then no, this would not strike any part of the moon. Kind of interesting when you think about it, how precise this would have to be in order for us to observe the moon from the Earth. Next one, a leaning ladder. A 20-foot ladder leans against a building so that the angle between the ground and the ladder is 72 degrees. How high does the ladder reach the building? So I'm going to draw my building here. Maybe I've got to reach to this top window, and I've got to decide if this 20-foot ladder is going to be tall enough to reach this window. So I do know that the ladder itself is 20 feet, so I'm going to draw a crude ladder here. And I'm going to mark its measurement or its length with 20, and the angle measure to which the ladder forms against the ground, so against the ground and the ladder, is 72 degrees. How tall or how high does the ladder reach on the building? That would be our x value here. Well, according to our angle measure, x is an opposite side and 20 is an hypotenuse, so I can use the sine or the cosecant rule. I'm going to use sine here. Sine of 72 degrees must be equal to the opposite side, which was x, divided by the hypotenuse length, which was 20. So x is equal to 20 times sine of 72. X therefore is equal to the result of that calculation, so 20 times the sine of 72 comes out to be that wild radical symbol, or in decimal results 19.0211 feet. 19.0211 feet. 53. The elevation of a kite. A man lying on the beach is flying a kite. He holds the end of the kite's string at ground level and estimates the angle of elevation of the kite to be 50 degrees. So he's down on the ground here, and our kite is up in the air, and we assume that that angle measure is 50 degrees, and this is the ground. Our question becomes, how high in the air is that kite? X units. Now the string itself is 450 feet long. Now, if you've ever flown a kite, you know that the string itself doesn't stretch perfectly straight here, but we'll go ahead and assume that it is straight. We're not going to worry about the curve that would occur because of wind resistance or gravity. So we've got a straight line kite here. We know that 50 degrees is established at the angle of elevation. This x represents the opposite side of a right triangle, and this 450 represents the hypotenuse. So the rules that use opposite and hypotenuse are sine and cosecant. I'm going to use cosecant this time just to get the extra practice. Cosecant of our angle measure, 50, must be equal to the hypotenuse, 450, divided by the opposite side, which was x. So x must be equal to 450 divided by cosecant of 50 itself, and therefore x would be equal to the result of that calculation. 450 divided by, let's get rid of that, divided by the cosecant of 50 degrees. That comes out to 344.7199 feet. So let's call that 344.7199 If I needed to round that to 4 decimal places, that's what that result would look like. And if I used the sine function and switched or the inverse of the ratio here, then the result also would have come out to be 344.72. Let's look at this last example here together. The height of a tower. A water tower is located 325 feet from a building. From a window in the building, an observer notes the angle of elevation to the top of the tower is 39 degrees, and the angle of depression to the bottom of the tower is 25. Remember, when we look upward, that's an angle of elevation, and when we look downward, that's an angle of depression. They both create right triangles, so we can establish the opposite side lengths, x and y, or a and b. I'll use x and y here. Our job is to determine how tall the tower is, and we can also figure out how high in the air the window is as well. That's pretty easy to figure out because we'll actually establish that along the way. Now, the total height of the tower, we'll call that h. Let's remind ourselves that h is going to be equal to x plus y in this case. Once I find x, once I find y, I'll add those together, and that'll represent the total height of this tower. So let's work on x first. I have an angle here, 25, and the right angle here in this corner. That makes this side length an opposite side. And we have the length, or the distance from the building to the tower, at 325 feet. Now, even though that was measured down here, because this essentially forms a rectangle surrounding our triangle here, and rectangles are parallelograms, then I know that this side length is also 325 feet. So that gives me an opposite side and an adjacent side. Let's use tangent to solve this one. Tangent of 25 degrees must be equal to the opposite x divided by the adjacent 325. So therefore x is equal to 325 times tangent of 25. So 325 times tangent of 25 is 151.5499, or 5500. X is equal to 151.5500 feet. Now, incidentally, since we just identified what x was, since we found x right here, that height is also the same height as this measurement from the base to the building. So how high is the window? The window is 151 feet in the air. Let's go ahead and keep moving forward and find y this time. The opposite side length here is y, and we have an adjacent side length, 325, given to us, so we can use tangent again in this case. However, we're using tangent of 39 degrees, which is equal to our opposite side length, y, divided by our adjacent side length, 325. So y must be equal to 325 times tangent of 39. Y therefore is equal to 325 times tangent of 39 degrees, and that comes out to be 263.1798. 263.1798. So the side length x and y added together would give me my total height. So the total height of this object, or of this tower, is 263.1798 plus 151.5500. 414.7298. 414.7298 feet. So using a little bit of trigonometry, we found our total height here. Hopefully this week you've seen the value in this trigonometry and you're not too intimidated by just looking at the triangles themselves and memorizing the rules at this point. But the more you practice, the better you'll become at this, so I encourage you to continue to practice. Be sure to ask me any questions if you have them during class time.